Hi, in this video we're going to find exact trigonometric ratios. In previous videos we've used sine, cos and tan in trigonometry to find unknown lengths and unknown angles. But usually we used a calculator, so we might have ended up calculating 6 tan 47 degrees and we just put tan of 47 into our calculator and it calculated it for us. But it might be there's like nicer angles of 45 degrees, 30 degrees and 60 degrees, and these are kind of nice angles we find in common shapes like squares and like equilateral triangles where we want to find sine, cos and tan of them. So how do we do that? Well, what we do is we have a unit square, so a square of side length 1, and we have an equilateral triangle of side length 2. And then we make a right angle triangle from them. So for this square, we're going to do a diagonal like this. And you can see in the square, like the angle here is going to be 90 degrees. And you can also see, because this 90-degree angle is cut exactly in half, that's going to be 45 degrees here. Yep. And we've also got this length here is 1. And then if we use Pythagoras' theorem, we could work out what this diagonal is. So let's do that. If we label the shorter sides as A and B and the longer side as C, then remember Pythagoras' theorem is that A squared plus B squared is equal to C squared. Now the A is 1, so we've got 1 squared plus the B is 1 squared, and that is equal to C squared, which we're trying to work out. So we've got C squared is equal to 2, and if we square root both sides, we've got C is the square root of 2. So we can see that this side length, if I just rub these out, this side length in the middle of that diagonal is root 2. Now we can then do trigonometry on this right angle triangle to work out what sine, cos and tan of 45 is. So this is the angle of interest. Remember, the angle of interest is the angle we know that's not the right angle. And then we label the sides relative to this angle of interest. So this side here is opposite that angle of interest. So that is O for opposite. This side here is adjacent to, next to that angle of interest. So that's A for adjacent. And then this other side is a hypotenuse. It's the longest side of the triangle. So then we can use our trigonometric ratios. Remember how these work? That you've got the angle of interest, theta, that's just a Greek letter theta, often used for unknown angles. And these are the sides, the opposite, the adjacent, the hypotenuse. And we have these three kind of magic functions, sine, cos and tan, which takes an angle as the input and gives you the ratio of sides between two of the lengths. Now, let's use this for each of these. Let's first work out what sine of the 45 is. Well, sine of this 45 here, we saw sine is opposite over hypotenuse. It's opposite over hypotenuse, 1 over root 2. So sine of 45 is 1 over root 2. So let's put that in our table. Sine of 45 is 1 over root 2. We can also work out cos of 45. Well, looking at our ratios again, cos of 45 is A over H, which is here 1 over root 2 again. So it's the same value. So that's 1 over root 2. And what about tan of 45? Let's do it over here. Tan of 45, if we look at our table, tan of the angle is O over A. So it's 1 over 1. That's this one here over this one here. 1 over 1 is just 1. So tan of 45 is 1. So we use a unit square and break it in half in order to work out what sine of 45, cos of 45 and tan of 45 is. But it might be worthwhile memorizing these values. Now, what about 30 and 60? Well, we find angles of 60 in an equilateral triangle, don't we? So start with an equilateral triangle side 2. And the reason I'm going to make it side length 2 is because then if I split it in half like this, got a right angle triangle. Remember, an equilateral triangle, each interior angle is 60 degrees. It's 180 divided by 3 is 60. And this angle up here is just 180 minus 90 minus 60, which is 30 degrees. And how do we work out the other side lengths? Well, a full length of the equilateral triangle is 2. So that length across here is also 2. And this is half of it, so that must be 1. And that's why I made the side length 2, because then 2 nicely halves to give 1, so you don't end up with fractions. And then we need to use Pythagoras again to work out this other side length. So if we call these sides, the shorter sides A and B, and the longest length C, the hypotenuse, then we've got A squared plus B squared equals C squared. We've got 1 squared plus B squared, which is unknown. Let's call that X. So X squared is equal to C squared, 2 squared. And if you solve that, you get X is root 3. So this length going up is root 3 here by Pythagoras theorem. And now we can work out what sine, cos, and tan of 30 degrees and 60 degrees is. So if the angle of interest was the 30, then let's label the sides relative to 30. This would be the opposite because it's opposite the 30. This is adjacent to the 30, and the longest side is the h, the hypotenuse. And that means if we work these out, sine of 30 would be, using this table here, is O over H. O over H, which is 1 over 2. So sine of 30 is 1 over 2. Cos of 30 would be A over H. A over H, which is root 3 over 2. And finally, tan of 30 is O over A from this table. O over A is 1 over root 3. So we can put that into here. We got sine of 30 is equal to half. Cos of 30 is equal to root 3 over 2. And tan of 30 is 1 over root 3. And then we can do the same for the 60 degree angle. So if I just not unhighlight that 30, and then instead the angle of interest is a 60, I need to relabel these sides now. So this side now is opposite to the 60. So that's the opposite. The 1 is adjacent to, next to the 60, and this is still the hypotenuse. So then we can do a similar thing. So we can do sine of 60 is going to be opposite over hypotenuse, which is root 3 over 2. Cos of 60 is going to be adjacent over hypotenuse, which is 1 over 2. And tan of 60 is going to be opposite over adjacent, which is root 3 over 1, which is just root 3. And I can put these values again into our table. So this was root 3 over 2, half, and root 3. So this is our final table of exact trig values. And as I say, it might be worthwhile trying to memorize that.